many biosignatures can survive. So things like porphyrins and quinones. How long could they last if they were left on the surface of Mars or on an asteroid by life that had once been there? How many years or decades or centuries or millennia could you expect them to survive? There's none of this that we do in the current experiment I'll tell you about today, but another part of astrobiology is looking for habitable environments. Obviously, you've heard a lot of the news about this recently, about planets that look like they have environments similar to Earth, and the Kepler mission is finding those more and more. So this is all about fundamental understanding of life in the universe. In contrast to astrobiology, fundamental space biology is much more applied in a sense. It's the effects of the space environment on terrestrial life, and very much with an eye towards humans being explorers of space and how space will affect us and organisms that we take with us. So the two main effects are first microgravity or reduced gravity, depending on the situation. And in mammals, that changes fluid distribution, loading of your skeleton. It creates immune stress, which is significant. Bone density changes rapidly. Your pelvis and the load-bearing bones in your legs lose bone density at a rate of about 1.8% per month. So imagine osteoporosis, 2% a month in the initial months that you're in space. So all of us, as we age, eventually start to undergo osteoporosis that can become an issue. This, if you will, is an accelerated testing platform for osteoporosis. And some things have been learned about that in the space studies that may be relevant to many of us. Cells and microorganisms also are affected by reduced gravity, but it has more to do with transport of nutrients and waste than it does with skeletal things, so there are actually skeletal factors. The other significant parameter that's different in space than on the ground